Linear accelerators, or LINACs, are used in a variety of industrial and clinical applications, including package and food sterilization, polymerization, and the treatment of tumors. While the name LINAC is generally applied to the whole apparatus, it correctly refers only to that portion which accelerates electrons. The rest of the device is concerned with bending the beam, modifying the beam by collimating it or converting it into X-rays, or both, supporting the target in the correct location, and providing a power source, mechanical support, cooling, and motion control. The general arrangement has a gantry arm which holds the treatment head in the desired location and orientation. For low energies, a short inline accelerator waveguide can be used. This has the advantage of having the beam energized in the desired final direction and simplifies the design. For higher energies, and particularly those associated with medical treatment, the accelerator waveguide becomes prohibitively long and must be mounted in the gantry arm itself. In this orientation, the beam is energized approximately perpendicular to the final direction and must be bent to enter the treatment head. This is achieved by using bending magnets. The LINAC itself requires a source of electrons and a source of energy. The electrons are produced by an electron gun situated at one end of the LINAC. The acceleration energy is delivered in the form of microwaves produced by a magnetron or klystron and propagated down transport waveguides to the accelerator waveguide. In order for this system to work, the entire LINAC must be evacuated by a vacuum system. Further, because of the power levels involved, many of the systems, including the microwave generator and the accelerator waveguide, must be cooled, usually by a pumped water system. The electron gun uses thermionic emission from a heated cathode to produce a beam that is accelerated towards the anode, which is situated at the inlet of the accelerator waveguide. The cup shape produces an electrostatic field between the cathode and the anode that focuses the beam prior to entry to the accelerator waveguide. Steering coils, mounted as orthogonal pairs, control the inlet direction of the beam to ensure that it is travelling along the longitudinal axis of the accelerator waveguide. The steering coils work by deflecting the charged electrons in a controllable magnetic field. The electrons bend in a direction that is perpendicular to the magnetic field, so that the upper and lower steering coils steer the beam left and right, while those on the sides steer it up and down. Once inside the accelerator waveguide, the electromagnetic field of the microwaves filling the tuned cavities transfers energy to the electrons, accelerating them. It also has a tendency to concentrate the electrons into groups that pass through the accelerator as a bunch. To understand this, consider the forces on an electron in an electric field that varies sinusoidally with position. Electrons are repelled by negative electric fields and are attracted by positive ones. The electrons situated in the negative portion of the field will be accelerated to the right, with those in the most negative region being accelerated the most. The electrons in the positive region will feel a force to the left, which will decelerate them. The net effect is to produce a bunch ahead of the negative crest.